Hi guys, welcome back. We're going to talk today about continue our discussion of arrow pushing mechanism. So let me share my screen. So last time we talked about nucleophilic attack and loss of a leaving group. Right now we're going to discuss proton transfer reactions, which we discussed in chapter 3. So let's recall from chapter 3 that in a proton transfer reaction, a base with a lone pair, base with a lone pair, right here, attacks a hydrogen that's shown by the arrow. The base of the arrow starts at the lone pair and the head goes to the hydrogen. And again, since hydrogen can only form one bond, this bond has to break. And those electrons, you see the arrow is showing it going onto the chlorine. So the HCl bond is breaking. The oxygen picks up a hydrogen and you get that. And now chloride ion, okay? Down here, we show two forms of this. The complete form shows, in this case, water acting as a base, the lone pair forming a bond to hydrogen, the OH bond breaking is shown by the arrow. The electrons in the bond go on to the oxygen. And when this loses a hydrogen, it forms this compound, right? Plus H3O plus. Organic chemists, being fond of shorthand devices, have even a shorthand for this. So this is the same substrate we had over here. And the result of the reaction is this compound loses H plus, right? So sometimes chemists don't even show the base. They just show loss of H plus and what the resulting product that's formed when the substrate loses H plus, okay? So this is acceptable. The only time you don't want to write this is when you're asked to actually show the details of what's going on. In that case, you have to show the base involved and show the arrows. Here's another proton transfer. You have hydroxide as the base with lone pairs. The arrow shows the lone pair forms a bond to hydrogen. And then, of course, the CH bond has to break. And those electrons, where are they going? The arrow shows you that it's going onto the carbon, right? Going right onto that carbon. So you're left with this species over here. And why are there more arrows here? Well, this negative carbon has a lone pair of electrons, right? That is an allylic lone pair. That atom is attached to a double bond. And so you can get a resonance pattern, right? Allylic lone pair, which is two arrows. The arrow shows the lone pair going between the two carbons, forming a double bond here. And then to avoid this carbon getting 5 bonds, the pi electrons here have to move on to the oxygen, resulting in this, okay? So this whole section here is resonance. Allylic lone pair resonance. This is the proton transfer we showed in the first step. Okay, let's look at the next slide. Okay, so we're going to talk about rearrangements. So this is the structure of a carbocation. You have 3 groups attached, a methyl and 2 hydrogens. So the hybridization, the carbon uses sp2 hybrid orbitals, steric number 3. And remember, an sp2 hybridized atom has a p orbital. And there's the p orbital right here, right? This whole thing is the p orbital, right? And that p orbital is perpendicular to the plane of the molecule, right? All right. Let's look at this methyl group. Let's blow it up, and that's blown up here. You see the CH3. One of the CH bonds, we show the orbitals, the hydrogen 1s, and the sp3 orbital here on the carbon. This carbon is sp3 hybridized because the steric number is 4, right? It has 3 hydrogens and a carbon attached. Okay, so it turns out the electrons in this bond, in this orbital, can interact with the empty p orbital. See that? They're next door. See, this is empty. There's a carbocation, only has 6 valence electrons. This is an empty p orbital right here. And so when you have a carbon group next door, the electrons in the CH bond can leak into the empty p orbital and stabilize it. Okay? So carbocations are stabilized by carbon groups next door. And this is called hyperconjugation. Hyperconjugation. Okay. So based on studies like this, it's determined there's an order of carbocation stability, and that's shown here. So the least stable are just ordinary methyl carbocations. And then next, a little more stable, a primary. Why is this called primary? Because it has 1 carbon group attached to the positive carbon. And then a little more stable are secondary. Why is that called secondary? Because you have 2 carbon groups attached to the positive carbon. And the most stable are the tertiaries, with 3 carbon groups directly attached to the positive carbon. So the order of carbocation stability is tertiaries are greater than secondaries, are greater than primaries, are greater than methyls, okay? You should remember that. Tertiaries better than secondaries, better than primaries, better than methyls, all right? So let's take a look at these examples. So what this here, what is that? Primary, secondary, tertiary? It's secondary because you have two carbon groups attached, right? This one, only 1 carbon group attached, that's primary. This one has 1, 2, 3, so that's tertiary. Okay. Here, what's that? 1 carbon group attached, 2, so that's secondary. This one, positive carbons here, 1 carbon attached, primary. This one, 1 carbon attached, 2 carbons attached, 3 carbons attached, so that's tertiary. So you should be able to identify a carbocation as primary, secondary, or tertiary, okay? Okay. So what would this be? Right, you look at the positive carbon, you have 1 carbon here, 1 carbon here. That's all you have to worry about, what's directly attached. There's 2 carbons, so this would be a secondary carbocation. Okay, see how that works? Go back. It's a secondary carbocation. Now, carbocations, if they can, sometimes they undergo a rearrangement, and what drives that is a formation of a more stable carbocation. So let me give you, there's 2 types of rearrangements that carbocations undergo. One is called the hydride shift. So if you look at this carbocation, it's secondary, right? 1 carbon, 2 carbons. If you have a hydrogen next door, what happens is the hydrogen with the electrons can migrate over. So look at the arrow. You see the base of the arrow is starting at the electrons that make the CH bond, and the head is going to the positive carbon. So what that tells you is the electrons with the hydrogen comes along for the ride, migrate over to the positive carbon. This whole thing is migrating over, and there it is, you see? And so that leaves this carbon, it lost this pair of electrons with the hydrogen, so now this only has 3 bonds and it's positive. So what this hydride shift, H and a pair of electrons, this is a hydride ion, H and a pair of electrons. This is a hydride ion. This hydride shift resulted in a secondary carbocation over here becoming 1, 2, 3, a tertiary carbocation. So we went from a less stable carbocation to secondary to a more stable carbocation to tertiary. That's favorable, and so that will occur, okay? So whenever you can form a more stable carbocation by a hydride shift, it will take place, okay? There's one other type of shift called the methyl shift. So let's look here. So now you have a secondary, 2 carbons attached here. And now we have 3 methyl groups, 1, 2, 3, attached to the next door carbon. So what can happen here is you see the arrow, these electrons, the bond is breaking, and those electrons are moving to the positive carbon. And the methyl group that's attached to those electrons goes along for the ride. So the net result is this methyl shifts from this carbon to the positive carbon. See, there it is. And as a result, the carbon over here is left with only 3 bonds in a positive charge, okay? So we went again from a secondary carbocation to a 1, 2, 3 tertiary carbocation. Increase in stability, that's going to take place. Okay, whenever you can go from a less stable to a more stable carbocation, the reaction, the rearrangement, the shift will take place. It's a methyl move. It's called a methyl shift. Okay, and let's look at the next slide. So take a look at these carbocations and let's decide if they will undergo rearrangement. So this is primary, positive charge, 1 carbon attached. So don't forget, there's a hydrogen here, right? We need a 4th bond, okay? Right? So we can do this. These electrons are going to move over 1 atom. The hydrogen gets carried along with it, right? Let's show it down here. I'll show the hydrogen that moved. Excuse me. Okay. Now this carbon has a positive charge, right? And these are methyl groups here. So we went from a primary carbocation, and this is now a 1, 2, 3 tertiary. So that's favorable from a less stable primary to a more stable tertiary. So this is a hydride shift, and that's going to take place, all right? That's favorable. You're going to end up with this carbocation. Now in this case, we have a tertiary carbocation, right? 1, 2, 3. This is tertiary. As of now, we don't know of any more stable carbocations. So that's going to stay there, right? We can't do a hydride or methyl shift and end up with a more stable carbocation. So nothing happens here. That's stable. Okay. Let's go here. So now we have a secondary, 1 carbon here. Oops. Another carbon there. That's 2. So this is secondary. We have 2 methyls next door. What happens when we shift one of them? Okay. Let me draw that arrow again. So now the methyl with the electrons will move. What are we going to end up with? Well, we're going to have a methyl. The methyl will now be attached there. We'll have 1 more methyl here. So the positive charge will migrate there, right? Don't forget there is a hydrogen here. Carbocations have 3 bonds. We got 1 bond, 2 bond, and the missing hydrogen. And that hydrogen's still here. Oops, excuse me. So this carbocation with 3 bonds, it formed a new bond to this methyl that shifted. And this carbon now only has 3 bonds is positive. So we went from a secondary carbocation to a 1, 2, 3 tertiary carbocation. Secondary to tertiary is favorable, so the reaction does occur. Okay. So there's some good skill builder problems in the chapter 6 that give examples of all this, and they're definitely worth going over for practice. Okay. So let's look at this multi-step reaction, and we have 1 step, 2 steps, 3 steps, and 4 steps. And now that we've discussed the basic arrow pushing mechanisms, nucleophilic attack, loss of a leaving group, proton transfer, and rearrangement, let's see if we can classify each step in one of those categories. So what's the first one? So we have a lone pair, and the arrow shows it's forming a bond to a hydrogen. And then this arrow shows the HBr bond breaks. So the OH is picking up a hydrogen, see? So we're transferring a hydrogen. This is a proton transfer. The next step shows the arrow, the CO bond is breaking, right? CO bond is breaking. So these electrons move on to the oxygen. This is the product of that step. Okay. Now this only has 3 bonds. There's a hydrogen here. Don't forget the missing hydrogens. Okay, there's a hydrogen there. So this carbon is now positive. It's a carbocation. And so what has happened here? We've lost water. This is loss of a leaving group. The bond to a leaving group is broken. And the third step, you see the methyl group is shifting over here. I'll put the methyl in, CH3, and there it is now. That means this carbon, it loses a pair of electrons, is now a positive charge. We've gone from a secondary carbocation here to a tertiary one here. It's a favorable rearrangement. This is a methyl shift or rearrangement, right? And finally, we have a lone pair, a nucleophile, and the arrow shows it's forming a bond to the positive carbon. So this is a nucleophilic attack. It's not a proton transfer because the lone pair forms a bond to carbon. If it's forming a bond to a hydrogen, as we saw in step 1, then it's a proton transfer. But in this case, the lone pair is forming a bond to the carbon. Okay. So to review, first step is proton transfer, loss of leaving group, methyl shift, and nucleophilic attack. Okay. So a single step can sometimes include more than one arrow pushing pattern. And we saw an example when we were talking about early on in this unit. And here's another example of that. Here's a reaction which we'll study in the next chapter. You have a nucleophile with lone pairs, an electron-rich species. And the arrow says the lone pair is forming a bond to this carbon, which already has 4 bonds. And the second arrow here shows that this bond is breaking. So this is a nucleophilic attack. And this bond breaking is loss of a leaving group, right? The Br breaks off. Nucleophilic attack with this arrow, right? Loss of a leaving group with this arrow. Okay. Here's another example down here where more than one process is occurring at the same time. The OH with lone pairs is forming a bond to the hydrogen. So now we're talking about proton transfer, right? The hydrogen can only form one bond. So where are these electrons going? They're going down here. See that? See the arrowhead is pointing to the bond. So that's going to become a double bond. And this bond is breaking. See, these electrons are moving onto the bromine. So the bromine is being kicked out. So this is proton transfer plus loss of a leaving group. They combined in one reaction. Not uncommon that more than one process is combined in the same reaction. Okay. So finally, let's fill in the necessary arrows for the reactions below and identify the process involved. So let's look here what's happening in this first step. So you see where the hydroxides are reagent, and where it ends up, you see forming a bond to this carbon. See that? Everything else is the same. So you form a bond to the carbon. So one of these lone pairs must have attacked that carbon. And since this has 4 bonds, you can't have 5, the pi bond, pi electrons move on to the oxygen. So the basic process here is nucleophilic attack. Okay. The pi bond moving is incidental. The process is the lone pair forming a bond here. Why does it form a bond here? Because this is the positive end of a bond dipole. Right? And then the second step, look what's happening. You go from here to here. I'll draw that over. Let me draw that product here so it's a little easier to interpret. Okay. So what's happened here? This CO single bond has now become a double bond. So one of these lone pairs must have moved down here, right? Okay. Right. This group has been kicked out, right? It's not there anymore. You don't have a CO, CH2, CH3. So that's been kicked out. So this bond is broken, right? Let me erase this circle. Yeah. This bond is broken, and so that becomes O minus, right? So we formed a CO double bond, so the lone pairs come down here, and this bond breaks because this already has 4 bonds. So this is loss of a leaving group, right? What's the leaving group? This is the leaving group, right? So in these reactions, you have to pay attention to what takes place, all right? You got to inspect the reactants and products of the step and look and make sure you see what's happened. So in this case, a double bond is forming. So a second pair of electrons, it must come down here. And then this group leaves, so this bond must have broken. And the final step, you see, we start here. And these are the products. So what's happened? This carboxylic acid has lost a hydrogen. Oops. And this O minus has picked up a hydrogen. So that is a proton transfer. Okay.